In this particular example, we've been asked to take the derivative of the function y equals secant x divided by 1 plus tangent x. In this case, we've got to use the quotient rule in order to find the derivative. The quotient rule reads as y prime of x is equal to g of x, f prime of x, subtract f of x, g prime of x, all divided by g of x squared. So on the second line on this screen, that's what we've done. We've used the quotient rule. Y prime is equal to 1 plus tangent x, that's our g of x, times d dx of secant x, that means we will be taking the derivative of secant x, where secant x is actually f of x, so that will be our f prime of x. Subtract from that secant x, which is our f of x, times d dx of 1 plus tangent x. That derivative will be our our g prime of x. And then that's all divided by g of x squared, which is a 1 plus tangent x all squared. In the next line, we've actually taken those two derivatives. We found the derivative of secant x, and we've found the derivative of 1 plus tangent x. So we end up with y prime is equal to 1 plus tangent x, and that's all multiplied by secant x tangent x. Subtract from that secant x secant squared x. And again, that's all divided by 1 plus tangent x all squared. What we've merely done in the next line is we have expanded the expression. So we've taken the 1 plus tangent x and we've multiplied it by the secant x tangent x using the distributive property. So we end up with secant x tangent x plus secant x tangent squared x, subtract secant cubed x. The secant cubed x naturally is the product of secant x and secant squared x. And that is all being divided by 1 plus tangent x all squared. Then if you look in the numerator, you'll notice that secant x is common to all three of those expressions. So we common factor out the secant x, and we end up with secant x times, in brackets, tangent x plus tangent squared x, subtract secant squared x. And then that is all divided by 1 plus tangent x squared.